Okay, so we're going to continue with our energy talks. Today we're going to continue with potential and kinetic energy. Now we've already established that potential and kinetic energy are obviously two of our types of energies. What were our two kinds of potential energy?
Let's revert back to
Well, think about that as we talk about the law of conservation of energy. Okay, what does that law state, the conservation of energy law? This is one of those things I'm sure you've heard multiple times before in the past.
Is that what we like turn off our lights at a certain, or turn off all our electricity at a certain time?
No, that would conserve energy, but in this case, when we're talking about systems of energy you start off with and the energy you end up with.
energy.
If I want some energy, if I want electricity, okay, can I just conjure up some electricity
Oh no, you have to get it from somewhere.
through magic? Yes. And this is exactly what we're talking about. Magic does not apply here. The first law of thermodynamics says.
How do you pronounce that?
Thermodynamics.
You just said it.
I know, but like, say it again.
Thermodynamics.
What does thermo mean?
Heat.
Heat. What does dynamic mean?
Changing.
Changing, yeah. So our law just basically states that energy cannot be created nor destroyed. Okay, it can only transform from one type to another type. Alana?
Isn't that the same as the law of conservation of matter? Or
Yes. That's right. Now the amount of energy you start off with is going to equal to the energy you end up with. It's just like a math equation. Yes?
So, because like, we had the same amount of energy on Earth as we like, million years ago as we do now.
So the question was, we have the same amount of energy on Earth as we do a million years ago. Well, we're always getting an influx of more energy, right, from the sun. So, and from other radiation from around us.
So would it be like more of the universe has the same amount of energy?
So yes, you could say, theoretically, that the universe has the same amount of energy as we did when we started off with. And what is our source of energy on Earth? The sun, of course. Think about it, if we do not have the sun, first of all, the Earth would be a frozen planet. Secondly, it would be dark, which would mean there'd be no plants, which would mean there'd be no oxygen, which would also mean there'd be no food. So it would not be able to support life as we know it. Okay, so going back to our types of potential energy. What were our two types? Nigel? Chemical is a type of potential energy, that's right. But more specifically, for mechanical potential energy. Alana?
Thermal? Yes, sir.
Our stored energy?
I'll redact that statement.
Take two.
Electrical? It's closer. It's closer. Okay,
What do we have underneath potential energy? Your notes.
Oh. Gravitational or elastic.
That's exactly right. Gravitational, which is just our short energy based on how far your object is off the Earth's surface. Our equation is mass times gravity times height.
What was the definition of gravitational?
How far an object is, bless you, off the surface of, and I said Earth, but this could be anywhere. Because our gravity can't change. What's our unit for mass?
grams.
Importantly, kilograms. So unit for gravity.
Per second.
That's right. Meters per second. So unit for height.
Meters.
Water.
Meters. If we take mass times gravity, what is that going to equal? Newtons. That's exactly right. That's our force. Okay? So these two multiplied together are going to equal newtons. So now we have newtons times meters. Okay? What was our equation for work?
Work equals force times distance.
Yeah. Work equals force times distance. Is that what this is?
Yes.
Yeah, it's the same thing. Exactly the same equation. So that being said, what is our unit for potential energy?
Joules.
Joules.
Is potential energy the same as work?
Yes. It's the same equation, right? It just has different words to represent. It is broken down our force and mass and gravity.
It's all the exact same.
But it's the
I
same.
found the work and I found the potential energy as being the exact same.
Yes. Okay? So it's in joules. So, the higher the object, what's going to happen to our potential energy?
It's gonna,
Increase the height.
wait, what?
Increase the height.
Increase the height of an object. Difference between an object that's 2 feet off the ground or an object that's 20 stories off the ground. What's going to happen to the potential energy? Okay. That's right. What type of relationship is that? Directly proportional. What if we increase the mass of the object? What if we have a BB versus a bowling ball? Which one's going to have greater potential energy?
Bowling ball.
The bowling ball. That's right. Also directly proportional. What if we're no longer on Earth? What if we're on a planet whose gravity is 3 times that of Earth? What happens to potential energy? It also goes up. Directly proportional. They're all directly proportional. That's gravitational. Elastic, like a rubber band or a spring. Our equation is just the weight times the distance stretched.
Is there an abbreviation for distance stretch?
Just distance. So how is this similar to our gravitational equation? What's our unit for weight? Newtons, always, right? So this is newtons times
Here.
meters.
Wow.
Same equation again. So what's our unit?
Joules.
Joules.
They're all basically the same.
Work and energy. Remember, because it takes energy to do work, right?
But the way to come by the answer is different for each, right?
Not necessarily. Because look, you're doing the same things, and some are broken down more than others. Like weight is already one object here or one variable in elastic. Whereas in gravitational, it's broken down into mass and gravity. That's it. One extra step, but it's the same thing. Yes, right.
So, if I only have the work done, I would already know what the potential energy for elastic and gravity were.
Yes. But it will be one or the other, right?
Oh yeah, it'd be one. or the
Yes.
other, but yes.
Yes. So if we increase the weight, what's going to happen to our potential energy? It's going to increase. Directly proportional. What happens if we increase the distance stretched?
It's gonna go up.
It's also going to increase. All those directly proportional. Question?
So for all those, are they all going to be directly proportional, or are there going to be even?
Well, the question was, are all these variables going to be directly proportional? If they're on the same side of the equation, then they're going to be inversely. Take, for example, elastic potential energy. If the weight increases, what's going to happen to the distance stretched if our potential energy is constant? It's going to decrease. So in those cases, they'll be inversely proportional. So if they're on the same side, like any of these variables on the gravitational, the mass increases, potential energy is the same, then one of these other two are going to have to decrease to offset that. Good question. Okay, moving on. All right, so let's talk about kinetic energy. Our equation is half mv squared. Take half the mass, multiply it by the velocity squared. Order of operations. When you're calculating your kinetic energy, what do you have to do first? Exponents. So you have to square your velocity first. So if we increase the mass, what's going to happen to our kinetic energy? It's going to go up. If we increase the velocity, what's going to happen to our kinetic energy? It's going to increase as well. Directly proportional. What's your unit going to be? It's also going to be joules. That's right. Your unit is going to be joules for kinetic energy as well. Of these two variables, mass and velocity, which one has a greater impact on the equation? Why velocity? Because it's squared. Yeah. Mass is halved, whereas that velocity is squared, so it's much greater impact. Think of two objects, a bowling ball and a bullet, right? A bowling ball is significantly more massive than a bullet is. Yeah, but because that bullet is traveling at such a greater speed, it has much greater kinetic energy. The unit is still joules. All right, so now let's look at some examples of the interplay of all these, kinetic and potential. Pendulum. Anyone know what this red donut is? It's called? Yeah, what is the white called? It's a specific name. It's the Bob. Bob. Yeah. Not Robert, but Bob. Now, so this shows this animation of pendulum going back and forth. And it has your 2 meters here, your kinetic and potential energy. This is resetting. The height that it travels, and down here it has the velocity traveled. Okay, at each point. So, where are your kinetic energies and potential energies equal?
There you go.
I don't know. Right there.
And right there too.
Okay, so where is that?
On that box, that's like the second box.
I don't think he's talking
Right in the middle of
he
there,
wants to know like what do you call it?
Right in the middle, between where it goes up the highest and straight down, right?
Yeah.
On either side. Okay, so that's whenever transformation is halfway. Where is your kinetic energy the highest? That's right, at the bottom. Think of this like a roller coaster. Okay? At the very top, you're at the top of the hill of the roller coaster. At the bottom, you're at the very bottom of the roller coaster. Okay? When's your potential energy the greatest?
At the top.
At the top. Top of the swing. Now, what is inaccurate about this?
It stops in midair.
Stops in midair. That's number one. What else?
Stops. For the last one. Then, right when it gets to the middle of the next swing.
Will this go on forever like this?
No.
Why?
Friction.
Friction. That's right. This is not taking into account friction.
But it won't stop right there. It'll stop down the middle.
So eventually, it will not be able to go up as high every time, right? Friction and energy is actually lost due to heat, of course.
But does
So-
it create electricity? No? Then how's electricity created? Yeah.
Depends on what you're talking about. What we make steam in one form or another, and it turns a turbine. And turning that turbine creates electricity. We'll talk about electricity in depth. We'll also shock each other when we get to that point.
Yay!
I know you can't wait. All right, here's another one. Okay, so we have our roller coaster, or whatever that is, and we have our potential and kinetic bars there.
Oh my god.
So where are you going to have 100% potential?
At the top.
At the very top. Will it ever get that high again?
No.
No. Notice the height that he travels, or she, or they, directly corresponds to how much potential, right? Because potential, what's the equation for potential?
Mass times gravity times height.
That's right. Mass times gravity times height. So it's all based on how high you are. What about kinetic energy? Where does the cart have 100% kinetic? Yeah, anytime that is, you can call this, I guess, the x-axis. Anytime it is right on the x-axis at the bottom, furthest down. Okay, let's look at another one.
Start low.
How's that possible? You sure? Watch it again. Watch it again from the beginning.
Well, if there's enough.
Somehow you go fast enough.
Oh, it starts off with
What does it start off with? Does it start at 0?
No.
No, it doesn't start, even though the animation starts where it looks like it stopped. Look at the speed right at the beginning. They're already going at 8 meters per second. So who knows, back over to the left here, they could have started on a hill way up here, right? And they just came down, hit a flat spot, and then we're able to go all the way up here. So look how much kinetic energy they already have.
Is that how roller coasters are able to do that? Like when you go up really high and you go down and you can go back up?
Yes.
Mr. Hanzo, we should play this roller coaster.
Our equation. Is this our initial kinetic plus our initial potential? It's going to equal our final kinetic and our final potential. Question?
I's and then F.
Yes. Initials and finals.
Why isn't it potential energy plus kinetic energy?
It doesn't matter. Could be either way. So, whenever we are going to do these, we are going to assume it's a perfect world without friction, and we're not going to worry about energy loss due to heat. We'll just say one side is equal to the other side.
Why
for our purposes.
why wouldn't we take into consideration that
Because we're not there. We're not going to calculate coefficients of friction and all that.
but then we just be calculating everything further into the box?
It's a friction of gravity.
Then if you don't have friction, then you have to revisit it forever.
That's why this is just conceptual. Nigel?
What is the time bar? Why are they doing it?
I think that is total measured energy is what I'm going with.
Oh, I thought there was 9.
If you have like 2 inclines that are both the same height and the same like degrees, if you just went down and went back up, it just gone over.
If there's no friction. In our case, no. I mean, in real life, no, it wouldn't, right? Because if you're on like a skateboard, you can only go up unless you're putting energy in yourself, right? You'll only go up so much. Because, once again, friction, energy loss due to heat. Friction everywhere. Alright, second law of thermodynamics, entropy. And this is exactly what we're talking about. Okay? Energy loss due to friction and heat. So the second law just states that energy will be lost, and loss is in quotes because it really isn't lost, but it's turned into an unusable form, therefore not helpful.
When you say unusable form, do you mean our technology can't use it, or it can never be used ever?
It is unusable in that system, whatever it is. Now, sometimes that unusable form can be recommissioned for something else, like, say, the heater in a car. So whenever we say loss, we just talked about this, it's because it is converted into heat. And here's our diagram. So the difference between going down packed snow, which is if you've ever done snowboarding or skiing, it's just super slick and you go super fast, versus powder, which will slow you down. So this skier's kinetic energy is converted into wasted heat. See you tomorrow.